Welcome to another instructional video from OWL, the wise choice in fiber optic test equipment. I'm Professor Jim Powers. One of the most basic and fundamental procedures of testing fiber optic links is setting an optical reference, also called zeroing. Most technicians realize that zeroing is a necessary part of optical loss testing, yet many do not understand exactly what zeroing is or why they need to set a reference. This video will cover the concept of a reference, why setting a reference is typically called zeroing, the purpose of setting a reference, the different methods used to set a reference, and using these reference methods in common link configurations. Taking a measurement of any kind involves comparing a starting value and an ending value, then calculating the difference. This measurement is then compared to a specification to determine success or failure of whatever it is that is being measured. In the case of measuring fiber cable loss, a technician must first connect a transmitter called a light source to a receiver called a power meter through one or more test cables in order to determine the starting value, which is called the reference point. The process of determining a reference point may have different names in different industries. In fiber optics, this process is called zeroing. In the early days of optical loss measurement, technicians had to manually record reference values and fiber measurements on a piece of paper, then perform loss measurements by hand. Nowadays, most optical power meters are able to record the reference point internally, so that when final measurements are taken, the power meter immediately performs the necessary calculations and displays the test result on its display. Remember that taking a measurement requires a comparison between a starting value and an ending value. However, in order for a measurement to be valid, both values must be based upon the same measurement unit. The most basic unit of optical power is the watt. We are familiar with this term since it applies to something we use every day, the light bulb. A good example of this is a three-way light bulb, which has three brightness settings, for example, 50, 100, and 150 watts. Of course, it goes without saying that we first have to know how bright 1 watt is before we can know how bright 50 watts is. The same goes for fiber optics, except the light intensities are referenced to 1/1000th of a watt, or 1 milliwatt. In other words, just as all light bulbs are compared to 1 watt, all fiber optic light sources are compared to 1 milliwatt. However, working with decimal points can be somewhat difficult, so fiber optics uses a logarithmic scale called the decibel, or dB, to make calculations easier to understand. When integrating decibels into the milliwatt scale, we end up with a measurement unit called dBm, which is also referred to as decibels referenced to 1 milliwatt. So if 1 milliwatt is the reference for all fiber optic light sources, how does this translate into dBm? We can use a number line to look at this problem logically. Remember, the whole goal of measuring optical power in dBm is to see how much brighter or dimmer a light source is to the 1 milliwatt reference point. Thus, power greater than 1 milliwatt and its associated dBm value goes on the positive side of the number line. On the other hand, optical power less than 1 milliwatt and its associated dBm value goes on the negative side of the number line, and a minus sign is placed in front of the dBm number. Now, consider a 1 milliwatt source. Since this is exactly the same as our 1 milliwatt reference, it is neither positive dBm nor negative dBm. So logically speaking, the only value that remains is 0 dBm. It is important to note here that negative, as it relates to the dBm scale, does not mean the absence of light. It just simply means the light is dimmer than 1 milliwatt. This concept hints at why we call setting a reference zeroing. The first important concept to remember here is that whenever a light source output power is exactly the same as its reference level, comparing these two values will result in a decibel value that is zeroed. To help reinforce the positive, negative, and 0 dBm concept, the sun, moon, and stars can also be used as a helpful real-world example. So for argument's sake, let's say the full moon on a clear night represents 0 dBm. Sunlight might be positive 20 dBm, since it is much brighter than the moon. Venus isn't nearly as bright as the moon and could be minus 20 dBm. Normal stars might be minus 40 dBm, and finally, stars that are barely detectable might be said to be minus 70 dBm. Up until now, we have been dealing with optical power measurement, which is a measure of the actual brightness of a source. Carrying this concept over to optical loss measurement, which is the difference between two brightness measurements, the starting value is the output power of the test light source as measured through reference cables, and the ending value is the power measured through the link under test. Most optical power meters will have a button or process by which the reference level is recorded internally. As we have learned, the reference level is always the starting value in our loss equation. The ending value in this case would be the reference level after the power meter has internally recorded the reference level. Comparing these two values results in a measurement of 0 dB, which is the same as saying the power meter has been zeroed. Notice that the M has dropped off. In this case, you are no longer interested in the actual brightness of the source, but you are more interested in the difference between the reference level you started with and the light level you have after you have set the reference. In effect, this cancels the M's out, and you are left with only dB. This is another important concept to understand. When comparing two separate dBm values, the M drops off and you are left with a measurement unit called dB. Once the reference has been set, the power meter and light source can be connected to opposite ends of the link under test. When this is done, the power meter measures the received optical power, compares it to the reference level, and automatically performs the necessary calculations. The resulting test result is the optical loss of the link in dB. In order to set a reference, the power meter and light source need to be connected together somehow. How they are connected together depends upon the configuration of the link under test. Primarily, the reference method is determined by whether or not the ends of the fiber link are installed into patch panels. However, there may be other scenarios that affect the choice of reference method as well. The TIA 526 cabling standard outlines 3 different reference methods based on how many reference cables are used: 1 jumper, 2 jumper, and 3 jumper reference methods. The most common reference method is the 1 jumper method, where 1 patch cable is inserted between the power meter and the light source. This method has become the recommended reference method in recent years. The 2 jumper method uses 2 test cables, 1 for each tester, with a mating sleeve in the middle providing the connection between the 2 reference cables. This method was the preferred reference method many years ago, before it was determined that the 1 jumper method was a better choice. The 3 jumper method adds a 3rd test cable and a 2nd mating sleeve, where a 3rd cable is inserted between the 2 reference cables attached to the testers. This is the least common of the 3 reference methods. Now, here's another important concept to understand. For best results, never disturb the reference cable setup until testing has been fully completed. This ensures that the reference power coming out of the light source is the same as when the reference power was recorded in the power meter. Well, there are multiple reference methods to choose from. The basic test configuration should look like this: source, cable, mating sleeve, fiber under test, another mating sleeve, another cable, and finally the meter. Using this basic configuration, it will be easy to determine what parts belong to the link under test. The remainder will determine your preferred reference method. The first link configuration we will look at is typically considered to be an installed link. An installed link looks like this. The mating sleeves in this case are probably installed into racks and/or patch panels. This is by far the most typical link configuration. What remains are the two test cables, the light source and the power meter. The recommended reference method here is the one jumper method, where the test cable attached to the light source becomes the reference cable. Now you may ask, wouldn't it make sense to use the two jumper reference method since there are two test cables left over? The answer is no. Using the two jumper method would introduce an additional mating sleeve into the reference equation, and as a result would then introduce additional unwanted error into the final test result. In other words, the test would become less accurate. This is the reason the two jumper method is no longer preferred for this type of link configuration. Rather, simply check the power meter test cable first to ensure it is good and set it aside until you need it for taking the loss measurement. Then, use the light source test cable to set the one jumper reference. The second link configuration we will consider has a patch panel on one end and an open connector on the other end. This link configuration looks something like this. What remains from the test configuration is two test cables and a mating sleeve, exactly the pieces needed for the two jumper method. Simply connect the power meter and light source together with the two test cables and mating sleeve to set the reference. Once the reference has been set, disconnect one of the test cables from the mating sleeve. It doesn't matter which one, as long as you leave both cables attached to their respective test units. Insert the link under test between the single cable and the mating sleeve to take measurements. Now, you may note that the one jumper method can also be used here if the open connector on the fiber under test can directly plug into the power meter detector port. A diagram is shown here. The third link configuration we will look at does not include any mating sleeves in the link under test, so both ends of the fiber are just open connectors. This is typically referred to as a home run cable, but a patch cable also fits this description. So what remains from the test configuration is this: the source, a cable, the mating sleeve, another mating sleeve, the second cable, and finally the meter. Simply add a third reference cable in between the mating sleeves to connect using the three jumper method. Now you can set your reference. Once the reference has been set, remove the center patch cable and insert the home run cable or patch cable under test. Ultimately, it is up to the technician to understand how to look at the link under test and then choose the best reference method for the job at hand. This has been another instructional video from OWL, the wise choice in fiber optic test equipment. For more instructional videos, or to learn more about OWL's products in general, please visit owl-inc.com. I'm Professor Jim Powers. Thanks for watching.